there guys, how's it going? Mike coming back at you here with another video on vector calculus. In the previous video, we did a little bit of an introduction into differential forms. We went into why do we need these guys, what these things look like, and then also went through just some very basic operations that we can do with these differential forms. In this video, we're going to continue our discussion on differential forms, and we're going to see how do we want to view these guys? What can we do with these things? And this is going to be a fairly short video. We're not going to go too deep here with this, but we're going to see how these things relate to stuff we have already talked about in this course. So if we have some open set, which is a subset of R3, and we'll call this subset K, we can talk about 4 different types of things going on in K, or 4 different types of subsets of K. We could just be talking about a point, or individual points, say an ordered triple, x, y, z. We could be talking about an oriented simple curve. The curve could possibly be closed as well. We could be talking about an oriented surface, or we could be talking about an elementary subregion. Now, we've talked about differential 0 forms, 1 forms, 2 forms, and 3 forms. And what we really want to do is we want to get these guys involved and sort of think of these guys as functions of these 4 different subsets: points, simple curves, oriented surfaces, and elementary subregions. Well, if we look at the differential 0 form, which is just a real valued function, f of x, y, z, say, we can view this differential 0 form as a function of a point in the sense that if you take some point and we say plug it into our real valued function, we'll get out some real number. So this differential 0 form is a function of a point, some point in this subset K, and we get something in R. We get something in the set of real numbers. Now for differential 1 forms, 2 forms, and 3 forms, it gets a little bit more complicated. We can't just take a point and plug it in and trying to work these curves or surfaces or subregions into it doesn't quite work. So we have to bring the integral into it, and with bringing the integral in, we're going to see that we can take a curve, a surface, or a subregion and plug this into our function, and we'll get out some real number. So if we have a differential 1 form, it has the form, pun intended, p dx plus q dy plus r dz. Then we can assign a real number to any oriented simple curve C by taking the integral of our differential 1 form on this curve C. It's the integral over C of p dx plus q dy plus r dz. And this should look really familiar. This should look like something that we've seen before. We can parameterize our curve, x of t, y of t, z of t. T goes between 2 values a and b. Make that substitution in, and we just get the basic line integral formula that we saw earlier on in this course. If P, Q, and R were components of a vector field, that is, then this would be talking about the line integral of a vector field along a curve. But we see that, and we know from solving these problems that when we evaluate this integral, we always come up with some real number. So we're taking a curve, we're plugging it into our function, which we can think of is the integral around that curve of some fixed differential 1 form. And this integral that we get and that we evaluate, we get a real number in the end. So that's what we're doing with a differential one form. This is how we can view a differential one form as a function of a curve in this set K. So like, as we just saw, the integral of a one form assigns a real number to every oriented simple curve. The integral of a two form assigns a real number to every oriented surface S. The formula will look a little complicated, and it's going to look almost identical to the same as the formula for the flux across a surface in R3. It's going to look like it's the same thing, but it's not quite. There's one little thing that goes off, but it's very, very, very similar. So recapping what a differential two form looks like, omega p dx dy plus q dy dz plus r dz dx. When we have an oriented surface, we can parameterize our surface capital phi hat of u comma v. X, y, and z are each functions of u and v for some domain that's a subset of R2. We have the double integral over S of our differential two form omega equals the double integral over S p dx dy plus q dy dz plus r dz dx. And that's equal to the double integral over d of p times, and now this is the Jacobian matrix of partials of x and y with respect to u and v, plus q times the Jacobian matrix of partial derivatives of y and z with respect to u and v, and r times the Jacobian determinant matrix of partial derivatives of z and x with respect to u and v. So each of these guys here, these are all determinants of those Jacobian matrices. Now, if you were to look at the formula for the flux across a surface in R3, just as a quick recap, it's the double integral over S of f hat dot n hat d capital S. And if you look at these things and you make the substitutions, you'd find that it does look very similar, except it's not quite the same thing. What you would get in that formula would be almost the same thing here, but this guy is going to go there, this guy is going to go there, and then this guy is going to go here. So the order in which these determinants of our Jacobian matrices is thrown out of order. And that's why we say that it looks like the integral of flux, but it's not quite the same thing. Now, when we get a bit later on in this section, we will see how we get from this line here to this guy here. We're going to see why those dx dy changes into partial of x and y divided by partial of u and v, and so on and so forth. But we know from solving flux problems in R3 that what we have inside of our nice big set bracket here, this does all come out to be one number in the final end. So this integral of a differential two form is, again, taking some surface S, and we're taking the integral over that surface of some fixed differential two form, and we're going to come out with some real number. We can think of this as f of s right here. And just as a quick follow-up note, the result of the double integral over S of omega is independent of parameterization of our surface, capital S. So far we're seeing that, at least for the case of differential 1 forms and differential 2 forms, we can take either a curve or a surface in R3, take the integral of that object, or take the integral over that curve or surface of some fixed differential 1 or 2 form, and we get some real number. We're going to see that we can do the same kind of thing with a differential 3 form and an elementary subregion. So, lastly, just like all the cases beforehand, we can take the integral of a 3 form and have that assign a real number to every elementary subregion R. As a recap, a 3 form looks like omega equals p times dx dy dz. And if we take the integral over this subregion R of omega, we're taking the triple integral over R of p of xyz dx dy dz. And this formula should look really familiar. You've seen this in a previous class. This is just the basic triple integral of a function of x, y, and z over some 3D region, over some elementary subregion. So this is exactly what we talked about back in Calculus 3. But again, from Calculus 3, we know that this result is going to be a real number. So we can look at the integral of a 3 form over a subregion as a function of capital R. And we're seeing that for differential 0 forms, 1 forms, 2 forms, and 3 forms, we all saw each case where we can take one of our special subsets, a point, a curve, an oriented surface, or a subregion, and that can be the input of our function. In the case of a 0 form, our function is just the evaluation function. We take a point, our particular point that's in K, we plug it into a differential 0 form, we get a real number. For differential 1 forms, 2 forms, and 3 forms, we take the integral over this subset, a curve, a surface, or a subregion, and we take the integral over that subset of a fixed differential 1, 2, or 3 form, and we get a finite real number in the end. And there is a special term for a function that picks up some vector, that picks up something in a vector space and maps it to the scalar field for that vector space. The name for these things are linear functionals. So they're called linear functionals, or you'll hear the phrase dual vectors. If you go on to study more in the topic of linear algebra, you'll learn more about dual vectors and the dual space, and you'll get into more of the theory of what these things are. So this is as deep into linear functionals and dual vectors that we're going to go into here. But we can talk about integrals of a differential form over the appropriate corresponding subset, shall we say. We can look at these guys as linear functionals or dual vectors in the vector space R3 and its associated scalar field R. So this is the end of this video here. This is what I wanted to get into, just a little bit about the integrals of differential forms and how we want to view these guys. In the next video, we are going to look at the first of our operations that we need to understand involving differential forms. It's called the wedge product. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.